All right, week 104. What's up, everyone? Welcome to week 104 of building my own operating system. Um, Thanks a lot for joining. Let me just get set up real quick. Yeah, so last week was pretty good. We started on interrupts and we got a very, very initial basic progress point kind of milestone with that, going with the most absolute basic interrupt handler setup, where we were able to handle a divide by zero exception. And I'd like to continue with this kind of stuff today. So that's sort of the vibe. Yeah. Let me just make sure the tweet went out correctly and stuff, but looks pretty good. So yeah. Okay, got the mirror board as always. And is it time for another frame? Maybe. All right, that was kind of stupid. All right, I'll just draw another one. Four. Yeah, so I think I'm pretty excited about this week. We will definitely be getting into some assembly language programming, which is kind of rare. It's not something we do every day. But with interrupts, we have a nice opportunity to use a bit of assembly because we're going to need to set up our trap frame, which is kind of an interesting, very technical, and involves bridging from kind of raw assembly and ideally moving into C++. What's up, Yowdify? Does this run in Kimu? Yes. Just out of habit, I want to put the test 0 in the chat. Yep, totally running in Kimu. 100%. Okay. So, yeah. Maybe this is kind of stupid. Maybe it's kind of annoying to not have all these screenshots from last time around. So I'm just gonna do it here. Our goal for this week is to move forward with our roadmap here. Whoa. In particular, this part of the roadmap. So we got the basic assembly handler down, but now our goal by the end of this stream, it would be pretty incredible to have a C++ trap handler running, and to be able to handle things. Yeah. Currently, we only have a stupid infinite loop that just happens when you trigger an interrupt. And so we're going to try to push one step beyond that, construct the trap frame, and invoke a single interrupt handling path. Is this on GitHub? It is not currently. Maybe that will change in the future. But for now, this is just my private project. Okay. So let's just take a quick checkpoint in at where we are at right now. So the idea from last time, let's just clean up everything. So kmain cpp. I did a slight amount of work last time to make this a little bit more C++y. So I've, like I think last time we constructed the IDT, and then I was calling some methods or some functions to initialize it, and now I put it all into the constructor, and so I can pass an initializer list, and on construction of the IDT object, it will initialize all the entries, which I thought was kind of nice. And as always, none of this is necessarily production quality code. I'm still in what I would consider the prototyping phase of just getting this all to work in any way at all whatsoever. And so productionizing will come later. What's up, 711? Hi, bro. Any course based C++? Any course based on C++? Or, you know what? I actually don't really have anything to recommend for a C++ course, really. There's just all these YouTube videos of CPPCon talks. But actually, you know, I actually don't really know of a great course, to be honest with you. There's a lot of trainers out there. There's a lot of blog posts, conference talks. I'm sure there's some courses that I just never took one. What's up, Useless? It's good, dude. Yeah, nice to see you. Hope you're doing well. How are you doing? What's up, Nepali man? How do you start learning about OS? I took this course. I took this MIT course, and that was my first year of streaming, and I learned pretty much everything I know about OS development from that class. The Streamlabs thing is no longer inaccurate because we're no longer following that course, but that was the way I learned a lot of what I know. Okay, so just to trace the path, so what we're doing right now, we're still in our kind of raw, very prototyping the kernel, but we were playing around with some address space stuff. But really, yeah, I think this is just kind of remnants of when I was trying to make the kernel run on its own page tables, where we were trying to map actually, no, never mind. This is where I actually in preparation for some of the interrupt work, I actually mapped a stack region into the virtual address space of the kernel with the thinking that that would be necessary for interrupt handling. But what I realized is that for the interrupt handling we're doing right now, there are no privilege level changes. So there actually is not going to be a stack switch. And so actually this work I did to map a stack into the address space was not strictly necessary, but what it's trying to do is basically just map a region of address space that maps to the same physical memory that the stack currently is running on from the boot stack region. And then ideally, and then the thinking was that we would set a TSS entry to point to this new stack. We're probably not going to need that for the moment, so that's sort of dead code. And then we were just sort of basically had this interrupt descriptor table sort of thing. We install it and then trigger divide by 0 and observe what happens later. And if and then this is what we were seeing last time, and it's working correctly. We are seeing the kernel just sort of infinite loop when it hits the basic handler for the divide by 0, which is just showing that the basic handling mechanism is working. And so I'll just go over here, trap.s. Oops. Yeah, this is what we this is what I've pointed it to. And so what we're seeing here is I'm saying we want to register the 0th index in the IDT, make it point to the handle divide error function, which is defined in assembly here, and it is callable from, this is sort of weird with the, yeah, its descriptor privilege level is 3 for some reason, but in reality it should be 0. I guess I don't really know this DPL thing. I think it controls what privilege level you're allowed to trigger an interrupt from, I think. But in this case, it's a handle divide by error, so it's not really, I don't know if it's relevant to this interrupt. So question mark on the exact privilege level. I think if we go back to JOS real quick, we can see that it actually uses a 0 here. We use zeros for a lot of things, with a couple exceptions of the breakpoint exception and the system call, which are allowed to be triggered from ring 3. So maybe I'll just make that a 0 for now. Yeah. Useless, doing good. Finished writing part of a runtime mocking lib in C. Sounds hardcore, like mocking, like unit testing sort of thing, or runtime mocking. I guess I don't really understand what that means. Tugra, what's up? What's up, Tugra? Nice to see you. Also, what's up, Overshot Kuka? Hello. Okay, let me just do a quick check-in on the Git. Yeah, I don't know. Again, this history will all get totally cleaned up later. I think what is this doing? This is setting default values for some things in this struct. This is using this particular syntax, and then now we have some comments. So patch calls within functions to stubs. Okay, cool. Let me get our little timer going. Okay. Okay, let's begin. So, what's the first thing? Like, what's our roadmap for today? So, what are our micro checkpoints? We have our stupid infinite loop, and now we're going to basically just want to, maybe I will just work down here. We want to set up a generic ASM entry point that the stubs call into, and then call into C++. We want to define a trap frame of some kind. The generic entry point creates a trap frame and calls into C++. Doing good, just working. Nice. Stay on that grind. All right. So let's start. Let's come over here. So I also obviously need to get my documentation going. So got the Intel manual, flip over to the best part of the manual, which is volume 3, pop into chapter 6, and over here. So this is where we get, so we're trying to, for the moment, we're still handling the divide error No error code. Okay, so this is copied from JOS, but it's the no error code macro. And yeah, as opposed to okay, as opposed to the other one, I'm somewhat liberally copying from JOS for the moment. Right, so there are these two macros, trap handler and trap handler no error code. This was necessary for 32-bit, but let me review. I think it's the same for 64-bit, where some handlers some types of interrupts push an error code, some don't, and the idea is we want to kind of normalize this. And 64-bit does introduce some changes, but I think those are not relevant for now. One of the changes was that SS and RSP is pushed unconditionally. Which is not what I'm talking about right now. What's up, Abhishek? Also, what's up, Aswina Swin? Aswina Swin. Hi. Shadow stacks, blah, 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 blah. Okay. And then this is a related thing to what we're talking about. The unconditional push of SSRSP presents OSs with a consistent interrupt stack frame size. And also there, RSP is aligned. This is interesting. There's a change to the alignment. RSP is aligned to a 16-byte boundary before pushing the stack frame. I want to make sure I really understand that. And so it seems like it subtracts it. If it's not aligned on 16 bytes, it subtracts it down to the next 16-byte alignment, then pushes the stack frame. And as a reminder, where's our stack frame? Here's our stack frame. This is what we're going to be diving into today. Yo, what's up, Digitalized? Nice to see you, dude. Hey, but I'm thinking same project. Can you guide me where I should start and where I can get the resources? Oh, for sure. I'll just hit you with the resources page, and I'll hit you with the course, which is how I learned everything, and that's how I started. C++ is still worthy. Will Russell replace C++ in beginner? I like C++ and can proceed learning it. Rust will not replace C++. Yeah, hot topic. Yeah, I think if you like C++ and just like learning it, I think that's a worthwhile endeavor. I think it is still worthwhile to learn C++ even if you later moved on to Rust. personally, that's sort of what I'm sort of planning. I have a strong C++ background, but I think Rust is a great language, and I would someday like to learn it. But the thing is, having strong C++ knowledge will make it way easier to learn Rust, because Rust is basically an improved C++. So I don't think it's a bad trade-off to learn C++. If you like it, all the better. And if you learn C++, there's a lot of cool code bases you can potentially work on and contribute to, browsers, compilers, game engines. That's all C++. So I think it's not necessarily a bad bet. Although I do have to say, yeah, I mean, there are compelling arguments, I think, to not use C++ and to use Rust. In some cases, it's hard to ignore the benefits of Rust. Okay. Anyway, yeah. Yeah, so the things with the MIT link, you need to go to the labs tab, but then you find the labs. All right, so the Harvard link, there's no Harvard Harvard link. It's only the MIT link. This is just what I'm talking about, right? This is the website, most goated website in the world, and you just go and check out the labs, and you just do all the labs 1 through 7, and then by the time you finish them, you are pretty solid at OS programming. Is it your part-time thing? Yes, absolutely. It's like the most part-time thing in the world. It's only 2 hours a week. Yeah. Okay, trap handler, and so we're right now. So right, in the case of handling an interrupt that has an error code, all we need to do is push the trap number, and then we can jump into the all traps. In the case of the no EC, we have to normalize the stack, so we push the 0. I am just going to copy this. So I'm copying from Joss here to get this kind of set up because it is kind of finicky. So right, and now it's time to do the all traps thing. And yeah, without ripping too much from Joss, let's just see. Let's just try to do this from first principles. And so let's this is a good time to talk about and maybe think about our stack layout. Question, does this, I don't even really know how to do comments. Okay, cool. And so, RSP 16-byte aligned. And this is the existing stack frame the kernel was executing, or the whatever, for us, the kernel was executing. So we get 16-byte aligned, and then we're going to push, then it's going to be the error code, maybe. Then it's going to be the interrupt number / index. Oh, one of 2 parts, or you need a, yeah, exactly. Like it's so actually rare to be writing assembly, so this is sort of a special opportunity. And let's see if I'm up to the challenge. And so here's what we have so far. We're pushing the CPU either pushes the error code or we just push a 0, then the number, and then yeah. We basically need to save all the register state. And yeah, I am going to ask for some help from the AI, but I'm going to have it like try to not code. Okay, do not code. Change any files. What is the recommended way to save general purpose register state, e.g. when writing interrupt handling infra for an OS? Yeah, I'm just gonna, because I know there's this, on x86 there's this actual instruction that pushes a lot of the registers, but I somehow seem to recall, oh, what the hell? But I also seem to recall that people just do this manually sometimes. So I just think I need some help here, to be honest. Right, okay, yeah, let me correct this diagram. So there's all the CPU stuff first. I was wrong. And so stack point after transfer to the handler. This is exactly what we need. So SS, RSP, R flags, CS, RIP, error code. There we go. So this is pushed. All this up, then the error code. Okay. Disable interrupts as needed. Interesting. We are using an interrupt. Yeah, we can control whether it's an interrupt like gate or whatever. And so in this case, actually, I think we were almost always using interrupt gates, I think, which means it's going to automatically disable interrupts on entry. So we shouldn't have to worry about that part. Then save all GPRs with a single sequence and save segment registers if used. Treat that stack like that and pass, right. Okay, so that totally makes sense to me. Maybe let's start to very slowly create a trap frame structure. And I'm just going to kind of sloppily add it here because we already just have a file for this. Right, and this is here where we kind of need to do it like a bit upside down. I don't exactly know. Then we're going to have like GPRs are going to be here basically. And so that's going to be what's at the start. And maybe I'll make like some more structures. CPU. Data, I don't know what the naming is, but I basically just want to make a structure that describes the stuff that the CPU is pushing. And I'm kind of guessing, but I'm kind of guessing that these are all 64-bit. And so we know we're going to have we're gonna have our custom GPRs. Those will be the first thing in the struct because they're gonna be the bottom thing on the stack. And then we will have our CPU data. And yeah, again, I'm just completely sketching this out. This is all just this is all subject to change, but we'll make sure it's packed. GPR data, general purpose register data, and here's where it's going to be stuff like I don't know, like all the registers. Like, what are even the registers? I don't even know if I can type the registers out by hand. RAX, RBX, RCX, RDX, like blah, 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 right? That's sort of the idea here. And that's going to come first. Are you using Linux? No, I'm using Mac OS. I'm on a Mac right now. Yeah, I use Linux sometimes, mostly Ubuntu, like server when I need to have a Linux machine. But no, I'm on a Mac. Have a doubt? I guess the latter on you would be building GUI for your OS, right? Then you would use OpenShield. Else you would write your own thing for GUI. I mean, yeah, the GUI is super far away. Like, graphics is so far away. It's like, graphics is for me like the least interesting thing for the moment. There's so much more interesting stuff for the core kernel. Right. Context switch. On a context switch, you only save Kali, save. Oh, right. Since Kali is already on the stack. Well, let me see. So that sounds like a function call to me, right? That's sort of my understanding. It's like in a function call, the compiler emits code such that certain registers are saved and things. But in here we're not. Here it's I would say it actually is a context switch. We really need to save basically everything. The palm tree timer just popped up, which I'm going to take a 20-second. Be right back. Yeah, and so in the trap frame, I mean, so I would say I think this is a context switch, and we need to save all the registers because what's happening right now is the CPU has literally interrupted some completely random code that was running. And we're basically trying to invisibly interrupt that code, do something else, and then like transparently resume that code. And so we need to make sure to preserve the exact state that code is running in, basically. So, and that's why we need to save like basically all the registers. The question is, what are all the registers? Save all the GPRs. So I have a couple questions. And save segment registers if used, right? That's my question. Okay, so it's fairly clear to me why and how we would save the general purpose registers. I would need to sort of like look up like what they even all are, basically. I don't remember that off the top of my head. But the segment registers, like in JOS, I know it saves ES and DS as part of the, okay, without looking at the answer too much, where is the trap frame? Trap frame? So here's basically JOS's thing, and it has its general purpose registers, and then it saves ES and DS. And that's sort of what I'm curious about. And also, yeah, well, I saw the answer. We need, so an interrupt number. Or interrupt index or something like that, or, oh, yeah, whatever. Yeah. Yes, that's my understanding too. So let me just, yeah, let me just ask about the segment register thing. So, how do I decide if I need to save segment registers? I don't believe I'm using segment registers. I don't believe I'm using segment registers since I'm on 64-bit. So you generally, how far is through is bro? Not very far at all. We're at the beginning. I don't know. Yeah, no. We're setting up interrupts, which is not, yeah, which is like a very much beginning OS kind of task. Okay, segmentation is ignored. You generally don't need to save DS, ES, SS if you never change them. You should still be aware CSSs are implicitly saved. FS and GS do matter. Right. Okay, that stuff, yeah, that's sort of a bit tricky. But that can come later. That's more of a, using FS and GS is sort of a thing you can add later. I think this is more for like thread local data or CPU local data, something like that. So most OSs, okay. I think for the moment, we don't need, I'm just not gonna really worry about them too much. I think I actually don't really even know the state of them. Let me quickly just, let's pop open our protocol. All segment registers are loaded as 64-bit. Limits and bases are ignored. Okay, so the segment selectors are set to point to some of these descriptors or something like that. I think it's not that important. I think for what we're doing really right now, I can not really worry about that too much. That's sort of my guess. So yeah, right, just sort of, I don't know if it's confusing. So yeah, and then, okay, so then the next question is, okay, let's say GPRs. is pushing regs the best way to do it on 64-bit? I thought there was a single instruction on x86 that does this. This is like the push A instruction or something like that. Okay. Push A is only in 32-bit and is invalid in long mode. On x86 64, you save GPRs with explicit push Q move to the trap frame in a fixed order. Okay, got you. IT Gamer, should I read the Linux kernel book for operating systems development? I don't know, if you want. I personally have not really read a lot of books. I just sort of did what I said about taking this coursework and stuff like that. So can we pick up the GNU bootloader and start making kernel? Would that be helpful? Yeah, that's one way to go about it. With the OS coursework that I linked, they sort of start you off with a custom bootloader. I would say, yeah. I mean, honestly, yeah, I think Grub is like a decent option. I wouldn't really recommend writing your own bootloader, to be honest. I think that's kind of a distraction. It's sort of a separate topic even from OS development, and it just sort of gets in the way of getting to the interesting stuff of OS development. I think there's a lot of tutorials on the OSF wiki about how to use Grub for this. Or even better, I mean Limini, right? So Limini is the super popular bootloader that everyone's using these days. And I can see why. I'm literally using it right now. It's a good bootloader. And there's templates available for it. The problem is that there's like, you can follow the templates, but then there's no course like after that to guide you through it. And so you might get a little bit stuck there. And so, which is sort of why I just recommend this coursework, or find another course like the Harvard. Harvard has a good course. Other universities have good courses, and they have skeletons, OS skeletons you can use. Okay, cool. Now basically let's just find out what are all the general purpose registers on x86. That's like the main question right now. And I could literally ask the AI, but I sort of feel like that's I don't know, sort of getting spoon-fed a little bit too much. I feel like, so like maybe we can just go and check out the registers right here. So is there a 60? Okay, cool. So yeah, and so just trying to not rely on the AI to do like literally all my thinking. Let's check out what these registers are. I mean, alternatively, I could have maybe used the debugger. I could have done a, or even look at, I don't know if we have a register dump lying around in one of these screenshots, but that would maybe be another way just to figure out what all the registers are. And this is basically the big list: RAX, BX, RCX, RDX, RDI, RSI, RBP, blah, blah, blah. RSP, R8 to R15 are available. 8 to 15D represent new GPRs. Okay, so that's basically the list. Can I copy this? Can I copy and paste out of a PDF into okay. So like I'm just gonna kind of caveman do it right now. x, r di, rsi. So now it's saying rbp. Okay, now I want to be a bit careful because rbp and rsp, those are a bit special, but I'm just gonna put them there anyway. And then we have like r8 or whatever. Right. It's painful to learn every register. I was just learning with input with my brain, bust out after one chapter. Oh man. Yeah, too many registers for sure. Okay. Okay, so very roughly speaking, if I'm reading the manual correctly, these are the basic registers. We even got the handy table to help us. A, B, C, D, D, I, S, I. Okay, so limitations. Okay, I don't think we don't really need to worry about any of this. Operand size, blah, blah, blah. Okay. Okay, so that's pretty much it. So now, right. Excuse me. Okay, so what I can do now is just basically copy and paste this over here and add pushes for literally everything. I want to take 1 second to sort of stop and think about RSP and RBP, since those are kind of special registers. They're not exactly general purpose in the way the rest of these all are, just sort of like random storage locations. These actually have specific meaning, and I want to say, actually, I think we don't need RSP. If we're going back to look at JOS, it says useless, and the reason it's useless is because the CPU already pushes the stack pointer in the CPU data that it pushes. The only reason that JOS had to declare it here is because JOS was using the push A instruction. Let's try to find that. JOS, without looking at the answer for how to implement the trap handler, JOS was using the push A instruction as opposed to spelling out like 20 different push lines, basically. And that's why it was forced to declare an ESP, because push A has defined semantics in terms of what it pushes, and it apparently does it in this order, including ESP. And so it was forced to do this even though it's useless. We're not using push A, so we don't need to do that. We don't need to have irrelevant data. And maybe it's even worth a comment, not including RSP because it is already pushed by the CPU. Okay, and now RBP. Now this is sort of an interesting one. I think I just need to take a moment to think about this, but at first glance, I think it is correct. We do need to preserve RBP. RBP is, okay, bad stack diagram picture maybe. So right here's like the stack, and this thing is at some point this RBP is going to be pointing. This is going to be RBP, or what am I doing? The RBP is going to be pointing somewhere, right? The kernel is going to be executing. RBP is going to be pointing somewhere on the stack. There's going to be some kind of stack frame that it points to the top of. And then what's going to happen is the CPU is going to push is going to trigger the interrupt and then push all of the CPU data. And in our case right now, we are not focused on cross-privilege level interrupts. And the reason that matters is because it affects stack switching. Because if we were doing a cross-privilege interrupt, we would basically switch stacks. The CPU would switch to another stack, and then we would handle the interrupt on that stack. And I want to say we would take RBP and point it to a new place over here to begin the new, like a new stack frame for handling the interrupt. And then once we return from the interrupt, we would want to restore it back to where it was originally. And I'll check JOS in a moment just to see how it does this. I want to say I feel like it does it reset RBP? I think it has to. And so, but then what about now? So we're not doing cross-privilege interrupts. And so therefore it'll all be handled basically on the same frame, except I think we still actually do need to restore and save it. Because now RBP used to be running here. We're gonna sort of interrupt, push some data, and start our new interrupt handling frame right here. And to have this like work, we almost certainly want to have RBP pointing here. For the duration of the interrupt handling. And then at the very end, we want to revert it back to where it was. So that's my current guess. I'm going to say, yes, we do want to save RBP. We do want to restore RBP. Let's check out JOS to see what it does. And so let's just take a look first of all. That's sort of the thing. It does. I don't actually see it. All right. Feel free to join me for a 20-second stand-up and stretch. Yeah. So that's, to me, that's a little bit of an open question. Seems like JOS does not. It's a big question. Do we need to save and restore RBP? Yes, right? JOS saves EVP, but doesn't zero it out or anything when jumping into C. Yeah, interesting. What should Rust versus C? What should I focus on, Rust versus C? I mean, yeah. it's just sort of I think whichever you like more or whichever you find more interesting. I think there's reasons to learn both. Yeah. Yeah, C has a lot of memory safety problems and security problems. That's very clear. I think Rust is probably easier to kind of get into. And if you want to dive into C after that, that's not a bad path to do it. I think either order could work. I think it's more about what is inspiring for you. What lowers the bar. I think Rust does a great job of lowering the bar to entry. It makes it very easy to get started with programming Rust. So I think that's not a bad way to go about it. Do you need hardware skills and depth knowledge to do insane level of work like you? I mean, yeah, doing OS development definitely requires some knowledge of the hardware level, just in terms of like CPUs and the features they offer and how to interface directly with the CPU. Whether it's, yeah, in-depth knowledge. I mean, I think you necessarily need to have some level of depth for sure. Yes. Where did you learn C from? It's called Learn C the Hard Way. It was this book a long time ago that I used. Or this ebook. Are you working on how the CPU will interact with the hardware? Yes, pretty much. This is pretty much directly CPU interrupt handling, how the hardware, what features are in the hardware that allows the OS to handle interrupts. Yep. So this is kind of interesting, RBP. Maybe we can think through what's up with RBP specifically. So I think the interesting thing here is, let's just think through the stack a little bit. And so we're going to, oh, oops, okay. So there's the CPU data, right? But more generally, our trap frame is going to be here on the stack. We want to then call into a C++ handler function. And it's going to have like a function prologue at the start. And the prologue, oh, I don't know where my text box went. Okay, and the prologue is almost always something like, it's like push RBP, move, something, it's like push RBP, move, or RBP, RSP, move the stack pointer into RBP, and then sub, subtract the stack. Man, what is it? It's like you subtract the stack, like however big your stack frame is. RSP. I don't know. I don't even. Yeah, this is not like completely correct assembly, but that's a function prologue, and almost certainly. That's what our C++ handler is going to start with, something like this. And the interesting thing is, if we don't zero out RBP or something, I just want to quickly check out one thing in JOS while I'm thinking about it. So the other relevant part of JOS here is the entry.s, which jumps into the kernel on a very early part, and it zeroes out EBP before getting into things. And I'm kind of wondering if we want to do the same thing. I'm thinking that it's actually not completely necessary, but basically what happens is RSP is pointing here. We interrupt, a CPU pushes a bunch of data on the stack, whatever. And we're going to call into this function. And it's actually going to push this sort of random RBP on the stack, I want to say. So if I'm just thinking through how the stack is going to look, we're going to have the old RBP. Let's assume that we never cleared out the RBP. We're going to have this sort of like old RBP value over here, which is pointing here. And actually it's a call instruction, so we're actually going to have a rip here. But the thing is though, our interrupt handler return, like this function is not going to return in a normal way. Our handler function, and maybe I'll just sketch it out here. I'm just gonna make it inline, just handle trapper. I don't know what the name is, but it's gonna be some generic kind of function. It's gonna be just like a simple function, and it's going to take it's gonna take a reference, I think. Technically it's a pointer, but it's always like, we're always gonna have one. And so we're gonna say it takes a reference to a trap frame, and even a const reference if we want it to. Yeah, what's up, Hello Code? Nice to see you, thanks for joining again. Yeah, this function is gonna take a reference. I mean, maybe to really just simplify it and make it less confusing, it's gonna take a pointer to a trap frame. And it's going to do stuff, but the thing is, it's never going to have a return. We'll never do this. We will never actually return from this function. We're always, when we're done, we need to do a very specific sequence of instructions to iret out and return back from this. We'll be doing a custom iret return, basically. And so our custom iret return, it's actually going to be iretting back up here, CPU data, rip CS. Because remember, these are, it's like iretting back up here, I want to say. Let me, the manual, we were looking at this in the manual a little bit on a previous stream. The iret sequence is good to understand. So iret and IA32E. And so an iret must pop 8 byte items. So you need the iret queue or whatever. Okay, this is actually not completely explaining the iret. I mean, we even kind of looked at this in a previous stream. I think I just want to check out instruction set. So let's check out the iret. So iret. Trying to find the place where it talks about in 64-bit mode. This is crazy. This is wow. Okay, this is the part. IA32E mode. 32-bit operand, that's not what we want. Go to, wow, crazy. Return to same privilege level. Pops. It's really. Okay, this is hard to read. I wonder if there's an easier description about how to read this. Okay, I feel like it's very hard to even understand what this instruction does. I know it's some notion of it pops some things off the stack in a certain way, but it's very convoluted. I'm finding it very convoluted to figure out what. This is real address mode, which is not what we're using. I was hoping just to read it purely off of the manual. That didn't really work, to be honest. False, blah, blah, blah. Restart. Minimize. Oh my gosh. Okay, maybe it's not absolutely critical to figure this out right in this moment, but basically the whole idea is that in our function, we're not doing normal returns. We'll be doing a custom iret return. And the custom iret is going to figure out just how to handle this. And crucially, we're not going to be using any of this data, I think. The call instruction is going to push a rip, which we will never use because we will never want to return. It's going to be something like call handle trap or something like that. That's how it's going to look, but we're never going to want to return to continue executing code that's like after this. That will never happen. And so we're going to just kind of get a rip. It could even be a jump technically, but if we use a call instruction, we'll get a rip here that we will never use. The instruction will, since the compiler is emitting code, it will push a RBP that will also never be used. And this RBP will actually be kind of stale and pointing at this weird stack frame. So that would be an argument to zero out the RBP before we call into this handler function, such that it's like a 0. And we don't have this sort of stale pointer. That's like just a little bit, maybe that's a little bit cleaner. I sort of like that a little bit better than leaving this weird stale. Say, so do we clear the rip before calling into CPP? We don't have to. The pushed rip and pushed RBP will never be referenced, but if we don't clear it, it leaves a weird stale RBP pointer on the stack. So maybe it's cleaner just to clear it out before calling into C++. That's sort of what I'm thinking about that. Excuse me. Let me check the questions. When handling an interrupt, what part of the trap frame do you consider most critical for debugging errors? I don't know. I think it's all critical. Yeah, every part of the trap frame exists for a reason. So I'm not sure that any one part is more important. Pointer to pointer to pointer, like. What's up, Ismail? Week 104, let's go. Nice to see you. Nice to have you here as usual. Okay. Okay, so let's just zoom out one sec. I was just trying to figure out, what do I need to type here? Do I need, like, okay, obviously I need to do all my pushes. The question is, clear RBP? Maybe, I don't know if you can see where I'm typing. Yeah, so clear RBP? Yes, probably. And yeah, I'm just sketching out call handle trap. Pass trap frame pointer via register. Okay, quick 20 seconds. Feel free to join me, stand up and stretch or whatever. Okay. It's going to be something along the lines of move RDI RSP. I want to say, like on 64-bit, the first argument is passed, I think it's via RDI. Yeah, we need to double check that, but we just want to take the stack pointer, and that's the pointer to the trap frame. And so that's something like this: push all GPRs. Yeah, I think that's looking good. Okay, now let's vibe code it. So can I just tell it, please push all GPRs as defined in GPR data? And I just want to, it pushes from, yeah, I told it to not make changes, so now I'm asking it to make changes. The pushes are going to be like R15, it's going to be kind of in reverse order. So R15, blah, 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 blah. Yes, please edit. Changes are allowed. Now, it's going to be push Q, R15, like R14, like whatever the opposite order is. And let's just see if the AI can just do that. All right, IT Gamer, see you next time. Peace. Okay. Okay. I think it changed. No, is that it? Okay. So R15 down to R8, RBP, RSI, RDI, DX, CX, BX, racks. So that's looking great. Except, is that how you do it? Is that the right syntax? I don't even know what syntax we're using here, to be honest. I think it's AT&T. Is this file ATT syntax? I think it might be. Yeah, dang. That's because I think you use the percent signs for AT&T syntax. So how I want to not do that. I want to use Intel syntax, but maybe that's not the most important thing to do. Write that. We're talking about the DSA graph. DSA, what does that mean? Data structures and algorithms? Honestly, I don't know if I get the question, really. DSA graph. Honestly, I'm not like the best like graph programmer in the world. I haven't written like that many graph algorithms, to be honest. Okay, so we're pushing all these things. So here's what we're going to do. We're going to convert everything to Intel syntax. We'll do that at the end. That's like kind of important, but not the most critical thing in the direct path. How to clear RBP set to 0. How do you even do that? Is it like, obviously you can XOR it, or you can just move a 0 to it. Let's see what it says. XOR RBP, cool. And then move RSP into RDI. On 64-bit, is RDI the register for the first ARD? I'm pretty sure it is, right? Yes, RDI, RSI. Doesn't the debugger use AT by default? I think it might. I think it might. I think a lot of things use like defaults to AT&T. Yeah. Okay, yes, RDI, RSI, RDX, RCX, blah, blah, blah. So yeah, move RSP into RDI. I think it's, but we're on AT&T, so it's going to be in the opposite direction. Move RSP into RDI. And then call handle trap. I mean, I think that's actually how you do it. So I'm going to, I don't know, bravely see if this even works. That's sort of the idea. No, we're missing one thing. No, are we? No. So here was the idea. CPU pushes like these 5 things, and in the case of the divide by 0, it does not push an error. So our code manually pushes the 0. It we're also pushing the interrupt number, and then we're pushing all of the general purpose register state. And that's our trap frame. Easy to me. I'm trying to learn ARM for Cortex, and the calling conventions are completely flipped. Whoa. Completely flipped. What does it mean completely flipped? Like they're just different, or yeah, what is the ARM calling convention even? I don't even, it's been a long time since I even looked at ARM code, so I have no idea. Opposite of x86. But like, what's the opposite of this list? Like, if this is the x86 calling convention, what is the opposite of this? Like, don't they also just choose like random registers for things, or is like R0, R1, R2, R3, like that kind of thing? Okay, but we're like kind of close, I think. I want to say we're almost at a place where we can kind of test this. That's pretty much it. And now we would theoretically enter into some code here, and I don't know, I'll just like log like running inside handle trap. Then we'll do a while one or whatever, which I always like to do. Or we could panic. We could always just panic. I mean, panic is literally just these two things. So inside handle trap. So yeah. All right, let's just let's build and see what is broken. Handle trap undefined symbol. Okay. Because, okay, this is where we need to really have a source file, I think, because doing this in the header file is not going to cut it anymore. So it's no longer inline. You know, do I need the extern C? I don't really know. Handle trap. Now I need to edit the CMake lists to have a trap.cpp, I think. I must load the register first. Oh. All right, let's try compiling again. Oh, undefined symbol. So it is on. How did JAWS do this? Did JAWS? JAWS included things. Interesting. You have to do something like load R0, R1 to load value in. Oh wait, I see what you mean. Okay, it's like just like the ordering is like flipped, I see, of like which instruction, like the source and destination, right? I see. I see. To load R value into R1, but the thing is that's actually Intel syntax. It's like where the thing on the right goes into the thing on the left is Intel syntax, and then AT&T syntax is like that's flipped and like it can go the other way. So it depends on what syntax you're using for x86, which is like super confusing. What's up, Bruce Wayne? We got Batman in the chat right now. This is the resource that I used to learn about OS MIT course. And so JAWS actually included trap.h into this assembly file in order to obtain a really? Wait, no, what? How did it get? Where is the trap function defined, right? Trap, right here. I think that was a stupid grep. Okay, I feel like this is a dumb place to get stuck. Sorry. So I think I'm doing this wrong. So I think I need an extern C here on both place. Oh shit. Okay, so I'm just asking the AI. This is what the AI is good for. I am getting an undefined defined symbol error. Do read trap.h ppcpp and trap.s and debug it for me. I mean, I'm using extern. Oh wait, oh, this inline. Maybe that's the problem. Maybe that was the problem. Okay, yeah, no inline needed. Okay, you can stop. So, so now are we ready to test this or what? Yeah, what's up, filthy potato? What's up? I think we're ready to test this. And all we need to do is just run the kernel again. It's going to hit the divide by 0, and it's going to come here. And previously we were looping. Now we're going to actually run through this code. And if things like work, we're going to hit the panic. Okay, let's just go for it. Moment of truth. Yeah, look at that. Check it out. Inside handle trap. So that is interesting. I mean, it's actually, you know, it only says so much. Like we were able to get here, which all that means is that these things didn't crash. The real test would be, can we actually access the trap frame? So yeah. Dubs in the chat, please. Thank you. Got my bad little like crappy and handler trap function to run or whatever. The real test though is like, can we actually use the trap frame? And I think this is where I'm going to take the opportunity to convert it to a const reference, because it will never be a null pointer, because we're just guaranteed of that. Update function declaration. So now here's the part where I want to add a function that just sort of like dumps out and pretty prints. Please write a function that prints the contents of the trap frame using the log function. So this is sort of like boring code that I don't really care to write, but I want to just test that we're actually able to really access the trap frame, because that's gonna just make sure that we actually are properly passing the pointer and the data seems to match up. So, oh wait, why is it starting implementation? So I'm hoping it's gonna just add a function here that just goes through each of these things. Okay. Okay, let's check it out. Honestly, like, YOLO. let's just do it. I don't need this to be exported though. We can just make, that's sort of why I made the anonymous namespace, is so we can just put it in here. And why is all right, let's just run it. So now we're just going to do dump trap frame and pass the pointer to the trap frame, even though, yeah. Is there some oh wait, it's already a pointer. It's, or my, I don't know what, my, whatever, it doesn't really matter. So now let's just run, let's just compile and run that again and just check out what's going on here. So how does that look? Does that look right? Maybe. How would you even know? It's just a bunch of numbers. But so the reason I'm slightly pausing, because it looks a little bit odd actually. It's odd that there's just so many zeros everywhere, but it's also totally, that's maybe plausible, because at the point when we hit the divide by 0, okay, no, something's wrong. Something's wrong. CS should not contain this. Something is wrong. You can tell that CS should not contain this. This is clearly a kernel pointer, and it doesn't not make any sense for RIP to be 0. And so there's a bug. There's some mismatch between how the struct is declared and yeah. So let's just look at this a little bit more carefully. Okay, this part should be hard to mess up. How can we mess up? You know, this part should really be on point. The GPR data should be on point, I feel like. And this approximately looks correct. RBP is this value. I mean, if we want, we could even debug this. We could use the debugger to look at the register states and verify that things match up. That's probably a good idea, I think. And that might even be instructive just to look at. So we're just going to we're just going to register a breakpoint on probably all traps. And so now we're here in all traps. It's actually a little bit odd that we're here and not on the R15. But here's the part where we can take a break for 20 seconds, be right back. Yeah, so here's the part where we can do a read. And let's just check out the state of all the registers. Let's take a big photo. And now we can compare. So let's just check it out. Yeah, I mean, in real life, there's a lot of zeros. Racks, RBX are both 0. 29, E9, A, RDI is E, RDI is also E9. Nine. So this looks totally right, and so that sort of makes sense. And then we can see. Okay, that's pretty much all we can get from that. So the problem is not in this part. The problem is somewhere else, and I'm realizing I'm missing a packed thing. Also, I think it shouldn't make a difference. Interrupt a number. So how did that? I mean, that should have just been a 0, so that's a little bit hard to tell. But it's 0, and that just leaves us with the CPU data. So let's just verify how that looks. So here's how I've defined it, and there must be some bug in how I've defined it. I defined it this way. Let me just screenshot even this. Get it all together. So I defined it this way based off of this diagram. Specifically, oh shit. Okay. Specifically based off of this part. And I was thinking that RBP, RIP, RIP, CS, R flags, RSP, and that's why I defined it like this. And in this order. You can see that it's growing by 8 bytes every time. So it's all Uint64Ts. And then why? It would seem like there is an extra 0. Yeah, this is like messed up. This thing should be in RIP. This thing should be in CS. Oh, okay, what's going on with that? What's up, Doa? But how can you know what the registers are supposed to look like? I mean, I think you can't know everything, but you can have certain intuitions. Like certain registers need to have pointers in them, and kernel pointers have a certain look to them. They always have like all these Fs up there. CS is a segment register, and so it's going to have a low number. For the rest of these things, yeah, I don't know. Yeah. And the flags register, this sort of approximately looks like how I would expect the flags register to look. You can just see like random like kind of bits are set, and with like zeros in between or whatever. So it strongly seems to me like things are like offset by 1 somehow. And maybe that's I don't know. Let's look at the dumper code. I don't know, you can just like kind of vibe it out a little bit. Like this has very much this like has RBP and RIP vibes. You know, this has like flags vibes. Like, yeah. So check out this dump. I'm like a little bit sus on this dump frame, but RIP CSR flag, so that's not it. RSP and SS, so it is sort of just yeah. It seems like there is an extra. What does it seem like? It seems like it seems like there was an extra 0 on the stack. Or oh, it's the error. Wait, it's the error code. Wait, no, yeah, it's the error code. I forgot to declare an error code. So yeah, error code, maybe error code. That's why. Yes, I was so fixated on these parts that I forgot about the error code. The error code is sometimes pushed. So that's why. So that's the problem. And how do I exit? Okay, let's run that again. And now, okay, let's run the kernel. Now we should really see this. Yeah, this is looking much better. Now we need to tell it to update dump the function to print the error code. So yeah, now that was a mistake. Forgot the error code. Okay. So micro vibe coding it. Now look at this. This is looking good. So yeah. And so it's like the same thing as before. You can see this as pointer vibes, and now things are looking good. RIP has this nice pointer looking thing in there. CS has the 28 segment selector. Flags has like the flags. So that's looking good. And I would say it's kind of working. And just to be clear about what that means, what we have working is just the most basic form of a kernel execution being interrupted by like a trap in this case, because it's a divide by 0, so it's synchronous. And then the kernel execution gets interrupted, and instead of infinite looping like we did last week, now we are going a little bit further, and we're not infinite looping, we're actually constructing a trap frame correctly, and we're going to pass that off to be able to handle the interrupt from a nice, comfortable place in C++ where we have, variables and stuff and not assembly. So that's really nice. And it's sort of tempting to try to do a return. I wonder how fast we could get a basic return going. Let's just kind of think about what that would take. And so I'm going to schedule a function called void iret, or even like trap return or something weird like that. And this is, we're going to call, after we do the dump, we're going to call trap return. And trap return is it's going to be responsible for returning from the interrupt. And what does that mean specifically? It means that it's going to be responsible for like clearing out. No, it's going to be responsible for restoring registers. And doing the opposite of everything this thing did. And maybe I don't even know. Yeah. Maybe we'll write it in assembly. Maybe it's easier to do it that way. Jasa did it all in an inline assembly C function. Maybe that's nice. I don't really know. We can at least sort of think about what it should do. And so basically what should happen is RSP, so on the iret, RSP should be reset to here. And so the function can take in a trap frame or reference or whatever it does. I mean, really you should take a reference, but whatever, pointer to the trap frame. And conceptually, it's going to reset RSP to point to P trap frame, because we could be calling this from sort of like random places, potentially within the kernel, after, you know, we could be potentially several stack frames deep in the kernel. And we should be able to just IRAT from arbitrary places, I think. And so no matter where RSP is pointing to, whether it's like, whether it's here, or if we pushed a few more trap frames and now we're executing like some other subroutines, we just want to like force it to go back to here, approximately. Basically force it back to the trap frame, and then we can pop all GPRs, just do the opposite of these lines. I think basically that's just kind of it. Not strictly necessary, but is more hygienic to not have the call the code and handle trap push some random stale RBP. Okay, pop all the GPRs, which pops up to here. Pop the interrupt number, which was also sort of this like custom thing that we're doing on our end. And then that is going to return things to somewhat back to what the CPU pushed. And then here's the part where I need to figure out exactly what the IRET requires to be on the stack. And that's sort of what I have forgotten, or at least don't remember. So yeah. So pop the interrupt number, pop the error code, and then we're going to trigger the IRET queue. And if that's all done correctly, that is going to return execution back to right here. Execution resumes seamlessly here, if we do that all correctly. And then this original stream of kernel execution resumes as if nothing happened. It like hits the divide by 0, it like blacks out, and like it wakes up and it's back here. Basically, that's the idea. So that's the high level concept of what we're trying to do. And I have some questions. My one major question, what about C++ detours? So yeah, so C++ destructors. I think in C, it's a little bit more easy to just like whip the RSP, like whip the stack pointer around in sort of like random places. Like, 'cause when you do that, you like, I mean, this is something you almost never do in code, but writing the interrupt return for an OS is quite unique, where you want to just sort of potentially just like pop several stack frames at once, just like destroy them immediately. At least that's what JOS does. I don't know how other OSs do that. Alternatively, you could have some rule saying you are not allowed to IRET from deeper stack frames, and you can only IRET from the top level stack frame. But even still, I'm a little bit not sure about that. So basically, in C++, the problem with just ripping the stack pointer like this is that all of a sudden, all these stack frames are just sort of like destroyed. And usually in C++, a very important base expectation you can always have is that destructors will run for objects when their lifetime ends. So when a stack frame gets destroyed, the life, like it is this formal process, and it runs the destructors for all the local variables. And that's nice if you have locks or like are relying on destructors in any way. And if you, and it's very important that destructors be run when they're expected to. And so by ripping the RSP in like this and like diverting execution in sort of like this sort of very brute force way, as I'm proposing and as Joss does, destructors are not going to get run, and that's sort of a concern. So not super sure about that one. Either one, forbid trap returning from deep frames, or find some mechanism to run detours. That sounds very complicated. And so I think the first one is probably just the more practical way to go about it. Yeah. What's up, Bipin? YouTube over Twitch. YouTube over Twitch. I have to agree. I think more interesting people are on YouTube for this kind of content. At least if my follower numbers have anything to say about that. So I think we had literally no Twitch people today. So pretty much as usual. Yeah. All right. Let me just quickly check. Cool. Okay. No Twitch chatters today. Yeah. Okay. So yeah, that's the conceptual idea. Are you using AI to create this? I would say partially. I would say in a very limited way. And so obviously I do have my AI chat window over here on the left. Clearly I've been using it throughout this entire stream. I'm trying to not have it generate massive amounts of code that are important. I'm mostly having it answer questions for me. And then in the case of the dump trap function, that's really not an important function. It's just sort of like grunt work. And so I'm very happy to allow the AI just to generate that kind of function for me. But I'm trying to do all the hard work myself in terms of thinking and brain power and stuff. So, yeah. Okay. One or two, probably go with one for now. Yeah, tedious and not interesting work. Yes. And whereas the interesting work is thinking this through and writing these comments. Pop the error code. It's not a question mark for sure. Like the entry interrupt code is always going to make sure that there's like a slot for an error code. If there's no error code, it'll push a 0, and so we always just want to get rid of that. I'm wondering, so this is my working idea for how this is going to work, and it might be tempting just to actually have the AI sort of just try to do it. As far as I'm concerned, we've sort of thought it through now. The manual work of typing out like the inline assembly or whatever it is maybe a little bit less interesting. So maybe let's just do it one at a time. I wonder, what does the inline chat do for this? Okay. Yeah, this is like something I would not be able to code off the dome at all. If you like can memorize and like code inline assembly from memory, that is super impressive to me. That syntax is wild. Okay. Let's just see pop. So I'm gonna guess it's gonna have some inline assembly that just does the exact thing where we see on the right, basically. Pop, 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 like a million things. But I think it actually did that. It did that wrong. It did it in the wrong order. You know, I think the inline chat is a little bit stupider than the chat like on the left here. And so the reason it did this in the wrong order, so we pushed things from R15 to racks down. And so now when we pop, we want to go starting from racks and ending with R15. This is the wrong order. Start with racks. I'm gonna kill the palm tree. Okay. And now that's the right order. I think. So again, referring back to this diagram. So reset RSP here, pop this. And now the question is, we don't want to strictly pop. We don't want to pop into a register. We just want to basically discard the data. And so what I'm going to say is move RSP 16 bytes up. Basically, we want to just like, after all these pops, the RSP is going to point to here. We want to discard these two things. So we want to just sort of add 16 to RSP. And then now RSP is pointing at here. And here's the part that I just don't know. And I will ask, what stack setup does iretq expect? Similar setup that the CPU pushed on the stack? iretq expects the same frame the CPU would have created on entry in reverse pop order. Error code is not consumed by iretq, so you must remove it yourself. And that's exactly what we're doing right here. We are discarding the interrupt number and the return code. And so I think this looks right. Always rip CS and R flags. And that's what we have right here. Rip CSR flags. If returning to a lower privilege level, SS, RSP, and SS. The stack pointer must point at RIP when you execute the iretq. And I think that's what we've achieved as far as this line. Emit and iretq. So now we're pretty much ready to iretq. And in the final moments of the stream, let's just give it a try. Trap frame. Does the code compile? Okay, moment of maybe truth. All right, let's give this a run. So what are we expecting here? As always, we're going to hit the divide by 0. We're going to hit the dump function as we have done in the past. It's going to dump a bunch of stuff. We're going to hit the trap return. We're going to go through this very surgical sequence of operations that slowly kind of deconstruct the trap frame and do the opposite of what we did on entry into the interrupt. We're going to hit the IRET queue and we're going to resume seamlessly here. And we're going to wake up after we blacked out. I'm going to say resumed seamlessly. Okay. Let's just run it. Okay. Oh no. Fuck. Okay. Dude, I can't. Okay, as you can probably tell, that did not resume. I literally can't even close the window. I literally have to click the quit button like a scrub. Oh my gosh. Okay, so it's pretty obvious what happened there, right? Like, well, it obviously did not work, and it was just triggering, like the boot. It was actually wait, well, that was interesting. Yeah, it was just boot looping because like something obviously was like pretty fricked up. Okay, in the final, I don't think we'll have time to finish debugging this like right now, but at the very least we can step through it and see what happened. Okay, gonna be spamming SI step instruction, so keep your eyes over here. Push, XOR, blah, 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 call, step. Now we're in the handle trap. Okay, step. Wait, let me just think this with my brain 1 sec. So actually, I think I know the problem. And it was that thing that I was sort of saying before. We have this rip. Actually, wait a sec. I don't know. Rip and the old RBP. So when we call the handle function, we do all this pushing. When we do the call instruction right here, we're going to push a rip value, which points like to line 90 or whatever, which we will never care about. The code that, as we were kind of talking about earlier, the code that enters does a push RBP, and so that's what this old RBP is going to be. But now that I think about it, when we reset the RSP like that, it's going to handle that automatically by forcing our RSP to be right here. So okay, so I was thinking that these things would mess it up, but I think that's not actually correct. So let's just keep stepping. So now we so now we are like kind of entering. Can I actually do a list? Or like, there's some way to list the source code, but whatever, we don't need that. So now it's going to be calling into this dump trap frame function. I'm going to use next instruction actually. So I don't want to go into the call, but I want to go over the call. And I feel like we should have seen, so a bunch of stuff printed out. And now we just did the call. And so now we're going to go into the trap return. So I'm going back to SI again. So now we're going back into trap return. And now this will be interesting to see. Oh, okay, this is interesting. The trap return. Oh, I know what the, okay. Can anyone see it? Just curious, can anyone see what the problem is? Wait a sec. I think I know. Actually, wait a sec. I'm not quite sure. Okay. I thought. Okay, my guess was that the problem is. we were resetting RSP to like point to this thing. But actually no, this should totally be a pointer to right here, right? So let's just take a look at how this looks. This is kind of sort of interesting to see how trap return looks. So push. It has a fairly typical prologue. It pushes a bunch of stuff onto the stack. It does a normal entry into a stack frame. And then here's where it starts to hit our inline assembly. You can see that, okay, RDI is the pointer to the trap frame. Because we're in like a non-optimized build, it does a kind of stupid thing where it stores it into the stack and then pops it back out, that exact same thing back into racks for some reason. It's a very typical debug build sort of thing that you see. And then, so basically, so now we're moving, again, I think we're using Intel syntax here, I believe. So moving racks into RSP. And so now RSP should be pointing at here, which is at the start of this thing, at the start of a trap frame. So that actually does look correct to me. Now let's just keep stepping. And let's step all the way here. So now move RSP racks. After, let's just reg read RSP. It's, I don't know, whatever it is. It's like some random thing. Let's just print. We can see trap frame. Trap frame is 7D60. And so after I do one more instruction, RSP should be 7D60. So let's just do that. Now it's reg read RSP 7D60. And so that should have worked. So now RSP should be right here, at the pointing right at the trap frame. We can even like print out, I don't know, some, yeah, we can just dump the stack a little bit and see what is there. And these numbers look familiar. These are, yeah, these are like the things that we were seeing earlier. For example, 0029 E9, that's the typical look of how our dump looked, 0029 E9. So that looks correct to me. I think we are pointed straight at the trap frame. So let's start popping. So pop, again, eyes over here. Pop, 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 pop. So now let's take a now let's dump the stack again. So now we popped like a bunch of stuff. We have these two words on the stack, and so the idea is to pop both of them off, which is what we're trying to do with this add 16. So let's step one more time. So now we're at the iWrite queue, and let's just dump the stack one more time. Now we're pointed at this thing. So this looks a lot like, so our RIP, it's like the 165A thing. 165A, hex 28. So it looks to me like we are seriously pointed like right here, right at the RIP. And if the AI is to be trusted, it's saying iRet expects the same frame the CP would have created in reverse. So RIP CSR flags blah, blah, blah. Error code is not consumed. You must remove yourself. We did that. So the only thing that's like all I can think about is that like all of this seemed to work totally fine. So my prediction is that the IRET queue is going to trigger the reset. Something is like wrong. I don't know. Let's just see it though. So one more time. So this asks, we are right at the IRET queue. I'm going to do a step instruction, and I believe the machine will reset. Wait, what? Oh. Wait, whoa, no, whoa, check this out. No, the machine did not reset. We resumed. Our pointer is right. Oh, but our pointer is right at the div again, and so that's the problem. It wasn't a boot loop. It was like an interrupt loop. Like we hit the divide by 0, handle the interrupt, resume back at the exact same instruction that triggers the divide by 0, and just do that in a loop forever. That is interesting. That is very interesting because normally a divide by 0, like some exceptions, it's normal. Let me think. It's normal to like continue past them, or at least retry the instruction. For example, with a page fault, like the instruction triggers the fault, you handle it and then retry the instruction. And that's what we're seeing here. It by default, it doesn't skip the instruction. You trap during the instruction and then retry it. And so that is very interesting. and I'm trying to remember but for example, if it was like an interrupt or a syscall or something, that's not how that works in terms of a legacy interrupt or a legacy syscall via an interrupt. You want to proceed to the next one. I mean, yeah, am I missing code? Handle this. I mean, in like real life, if something hits a divide by 0, you kill the task. Like that's like a fatal, or you deliver a signal to it or something like this. But basically just like that's sort of like a fatal error in a program if you hit the divide by 0. In this case, I sort of want to force it to continue. And so for the purposes of just trying to get our demo to work where we continue after it, I do need something. The question is what? How? Yeah, I need to return back to this instruction, really is what it comes down to. But and okay, if we're talking hacks, I could literally hard code it to like rewrite the stack and point it to this instruction. That could be kind of fun. I want to just ask the AI what the actual what's up, Souks? Currently, okay, we hit a divide by 0. Handle the exception and go into a loop because we return back to the divide by 0. For the moment, I simply want to continue after the divide by 0, after the instruction that triggers divide 0. Apart from like manually rewriting the IRETQ stack frame with a hard-coded RIP, is there a better better way to advance the PC by 1 instruction. Yeah, genuinely have forgotten how that part works. And so you can't add 1, you must decode the, oh my gosh. So this is the option that I said, but the question, but how do other kinds of exceptions work, e.g. a interrupt instruction int 80, etc., int 80, where you want to return past the int instruction. Oh, for software interrupts, the CPU saves rip of the next instruction, so IREQ, and that's the whole deal. So for interrupts, it's kind of special. Interrupts handle it, so at the CPU level, the CPU pushes the rip of the next instruction. So when you iwrite back, you automatically iwrite back into the right place. For faults, like a divide by 0, at the CPU level, it saves the rip of the faulting instruction, so you iwrite back and retry it. So I don't really feel like converting this to all like work with a software interrupt, so I'm gonna go with the ultimate hacky move, which is to hard code this thing, and hopefully we could just get this working like pretty immediately. So what I'm just gonna do right off the bat here, I'm gonna say ptrap frame CPU data dot rip equals this sketchy number, and because there's no randomization, I'm like very much hoping that these numbers are stable. This is that thing, Ismail, that you were talking about in a previous thing. So in the spirit of doing insane hacks, we're going to smash our own stack, basically, rewrite the rip to point to exactly where we want to return to. And I think that should do it. And then we should return back here and hit the panic. So let's just run that. Bam! Check it out. Check it out. Resume seamlessly. There we go. So we officially did it. We hit the divide by 0, constructed the trap frame, handled it in C++, dumped the trap frame, and did an insane, hack to return to the right place without doing an interrupt loop. So that was very interesting. All right, so I think that's going to bring it to the end of today's stream, but I want to thank you all for watching. I also want to promote, I want to show you something. If anyone didn't know, I recently made a TikTok. So I've been posting content. I've been getting into posting shorts. So if anyone's on TikTok, feel free to smash the follow button. Instagram, offline mark. I'm posting shorts on there also, little clips, and so I'm trying to find the best moments, and then yeah, obviously lastly, YouTube shorts. So yeah, getting into that whole thing. Yeah, YouTube seems to have the most views actually, compared to TikTok, which would make sense because I have the most subscribers there. But yeah, so that's just a little bit of a heads up. If you like brain rot, short form content, yeah, feel free to follow me over on those platforms. But yeah, as usual, if you're enjoying this content, please go ahead and smash that follow button right now. and then you will be able to get more content like this resumed seamlessly interrupt stuff. So yeah, that's mostly it. I'll hit you with the Discord link if you want to hang out some more. We've been having some good conversations in there lately. So yeah, I think that's going to be it. Next week is going to be a pre-recorded stream, probably because I'm going to be in Brussels at FOSDEM, and I'm going to see some of you there, I believe. Ismail, I think I'll see you there. We're going to chill. That's going to be sick. So I'll do a pre-recorded stream for next week, and then we'll be back live the week after. So that's the plan. I think that's going to be, yeah, anything else to say? No, I think that's pretty much it. Yeah, we in Brussels. It's going to be a party. Let's do it. All right, cool. Well, I'm going to sign off, hoping you have a great week, and I'll catch you in the next one. Peace.